Good morning, everyone. Let's start our second day of this meeting, Math&Science. We'll have a lecture in the morning by Dr. Anna Hankin, and after we have a flash presentations. I'm pleased to introduce Dr. Anna Hankin of the Imperial College of London, who will talk to us about a very interesting topic, pitfalls and the characterization of semiconductor liquid interfaces. Dr. Anna Hankin is working in Departamento of Chemical Engineering in Imperial College. We have has her postdoc and the PhD in the Imperial College in the Department of Chemical Engineering. Dr. Anna has several publications in very relevant journals in the field of materials and the energy. Testing of and the expertise of Dr. Anna is electrochemical energy conversion, water split of CO2 reduction, experimental characterization of semiconductor electrolyte interfaces, microcinética modeling of photoelectrochemical process, designing, characterization and modeling of scaled photoelectrochemical reactor system, metal recovery by electrodeposition. Please, Dr. Anna, you can to start your presentation. Thank you for to accept our invite to talk about an interesting topic in our meeting.
Oh, thank you so much for the very warm welcome and for your kind invitation. I'm very excited to be joining you today. It's a real pleasure and an honor for me. So I just thought I would put up this first slide just to show the name of my research group and its web browser address in case you're interested to know more about what I do in my research group. So I am by training an electrochemical engineer. I actually did my very first degree in physics at Imperial College, and then I didn't move very far. I moved just to the building next to the Department of Physics, Chemical Engineering, to pursue my PhD. And that was on the topic of electrochemical waste treatment. So I was electrodepositing nickel out of some plating wastewater for 4 years. And then I actually left for a little bit to have a break. And then my boss invited me back to do a postdoc position because he had started this new, very well-funded project on photoelectrochemical reactor development. So this was back in 2011. And at the time, the design of upscale, so big photoelectrochemical reactors was really very new. Now, the sort of training I had in the research group is that you can't really design any system without also modeling it. And so the emphasis was not only on designing photoelectrochemical reactors, and at the time they were working with hematite photoelectrodes and some photovoltaic panels just to see how the device operates, but also to model it, to predict whether the design of the device is actually sensible or not, and what losses might occur inside. So I joined the early stages of the project, and during subsequent years, we had a lot of fun designing different photoelectrochemical reactors, which can be scaled in so many different ways. And that's because there are a lot of constraints on how these reactors need to be engineered, because they're sort of a hybrid between an electrolyzer and a photovoltaic device. They embody in them the constraints that are placed normally on two systems individually, But here, all of these constraints, so you have to get the light in, and you have to have your electrodes are very conductive, like in an electrolyzer. You have to harvest your products. So all of these constraints are now placed on this one system. And you can design it depending on what factor you have chosen to be the most important for a particular case. So for example, if you are concentrating the incoming light onto a small area, you don't need to scale up your electrodes so much. But if you're not concentrating your light and you want to have a large electrode area, how do you scale it? Do you scale it like a square, or do you scale it in one dimension only? So all of these questions were being asked at the time. And so my role at which I entered in this project was to start the modeling. So we typically use multi-physics modeling, so taking into account and the thermodynamics and the kinetics and the mass transport and the heat transport and transport of dilute species, calculating where resistive losses occur. So all of these things. And in order to model that, we need to know the kinetics of the reactions at the electrode surfaces. Now, that is not so difficult in the case of water splitting when it's not a photoelectrochemical reactor, right? You usually have two metal plates, and you can use the Butler-Volmer equation to simulate the currents. But in this case, we were utilizing semiconductor liquid interfaces. And so I quickly converged on some problems to do with modeling of the kinetics at such interfaces. And that's how I ultimately sort of serendipitously got into studying this all the pitfalls that you can come across when characterizing a semiconductor liquid interface. So just to sort of show you why it's important to do the modeling and why kinetics are very important, especially for photoelectrochemical reactors, I just want to show some of the outputs of the models that we actually get that help us in designing the devices. So one of the main issues is to do with the symmetry of the electric field between what's usually a cathode, so the negatively polarized electrode in an electrolyzer, and the positively polarized one. So you've got hydrogen evolving at your cathode, oxygen evolving at the anode. Now, in a standard electrolyzer, the electroactive surfaces at which the reactions happen, they face each other, so they're completely parallel to each other, which means that the electric field is uniform, except at the very edges. Now, the ions in the solution which complete this electronic flow circuit also flow uniformly between the two electrodes to maintain the reaction, which means that whatever reactant is being consumed at an electrode is replenished all the way along the electrode surface, and it's uniform. And so the rate of the reaction is not being limited by non-uniformity of this field. And so I've sort of shown in a schematic way to say that, well, the rate of the reactions is uniform along the electrode length, except at the edges where you have some concentrations of the electric field line. Now, because in photoelectrochemical reactors you have to get the light in, you're then constrained to either using transparent substrates, which sometimes are too resistive for scale-up, or you reorientate one of the electrodes so that the surface that absorbs the light is actually facing towards the outside of the reactor instead of facing the other electrode. So now you have a very non-uniform distribution of the electric field. And what happens is that the ions that flow between the electrodes to complete the circuit, they always choose the path of least resistance. It's the case for any charged species. And so what happens is that the reaction rates become higher at the edges of the electrode and become smaller in the middle. So what that means is that if you scale up this electrode, for example, you want to increase your area, you make the electrode longer, it's not going to result in a proportionate increase in current because of this limitation. And if you happen to want to use a photoanode and a photocathode, and this is like an extreme case scenario where you need to orientate both of your electrodes to face the outside of the reactor, the scenario is exacerbated even more. So the extent of the losses that occur due to these non-uniformities depend on some factors. They depend on the resistance of the electrodes. They depend on the resistivity or, well, conductivity of the solution, but they also depend on the magnitude of the current density that's actually being generated. So how large is the photocurrent? If this was typical electrolyzers, through which you'd normally pass something like several thousand of amperes per square meter, these effects would be enormous. But the one positive thing about photoelectrolyzers not having such high currents is that these effects aren't as bad as perhaps is illustrated here. But still, you need to be able to model the kinetics, photoelectrochemical kinetics at specific interfaces in order to actually predict when these effects become very pronounced and when they will start limiting reactor performance. So it really helps in the design of the reactor. So what we do is we always compare our multi-physics models, which we carry out in COMSOL multi-physics, to experimental measurements. So we have several reactors that are designed to incorporate upscaled electrodes. So on the top left is a reactor that houses a 10 by 10 centimeter hematite electrode, which we made by spray pyrolysis. And we compared some performance of a planar and a perforated electrode to see whether the perforations can homogenize the current. So the comparisons that we obtained between experiment and the model were facilitated not only by COMSOL multiphysics, which has a lot of embedded functions, but by accurately inputting the photoelectrochemical kinetics that occurred at the, in this case, hematite solution interface. So then we come to looking at the details of what happens at a particular electrode when you have photoelectrochemical reactions occurring. So this is a case of a photoanode and a comparison of the current density that you get in the case of illumination and in the dark. So the very point of shining light, right, is that you get a photocurrent way before at much less positive, in this case, potentials than you would in the dark. So hence the energy input from the sun is helping to decrease the energy requirement for the whole process. So you would need to supply less energy from the mains, and some of it will come from the sun. And if you can achieve the same analogous process on the, for example, photocathode, then you will not need any external energy input at all, and solar energy will be sufficient. So the total current that you always measure will be a sum of the photocurrent and the dark current. And the idea is to model the kinetics such that you can see at which point the dark current becomes predominant, at which point you know that there is no, that's it. That's all you're going to get out of the system in terms of free energy. So the photocurrent itself can be predicted. It can be predicted using something called the Gertner-Butler equation, which takes into account things like irradiation intensity, the absorption coefficient of the semiconductor, and band bending, which is very important. So essentially, the photocurrent is proportional to the square of the band bending of the semiconductor at the semiconductor liquid interface. But the point at which you start to analyze the kinetics, so the sort of theoretical potential at which you have no kinetics, after which photoelectrochemical reactions become possible, is called the flat band potential, right? So it's a very important parameter in modeling the kinetics. So, and that's why so often in publications, the value of the flat band potential is quoted, because if you're able to change that and bring that, for example, to more negative values, then that's an achievement, because it means that you have earlier photocurrent onset. So incorporating this flat band potential into the model is essential. And that's where I first experienced the pitfalls of actually trying to find it. And after finding the flat band potential, you can then assess how the observed kinetics are different to the predictions. So the theoretical predictions are represented here by the black line. And then you have two major sources of losses. So one is bulk recombination. So it's a constant factor by which the number of electron hole pairs are decreased in the bulk. And then you have something called surface recombination, which is dependent on the extent of band bending at the semiconductor liquid interface. So the higher the degree of band bending, the smaller the recombination fraction of charge. And of course, you want to minimize surface recombination and get maximum current out. And so my colleague and I, Dr. Frankie Bedoya-Lora, together we worked on piecing together what is happening at the semiconductor liquid interface. So I started a bit before him, so I worked on the flat band potential, and subsequently I'll show you he took over with the actual determination of kinetics, how to work out these recombination fractions, both for the bulk and for the surface. So I don't want to sort of litter the slides with lots of references all the time, so I'll just put some references here. So before the dashed line are the publications that Frankie and I have published on this topic, looking at it from different angles, sometimes looking only at small scale material samples, and sometimes looking at how the models apply to upscale systems. And then there are a few others, a couple of others that we were particularly influenced by, so including one by Laurie Peter and Dino Klotz, who has done a lot on interfacial investigations. So I'll leave those there and I won't mention them too much more. So the flat band potential. So I think everyone has heard of it, and there are very standard way of measuring it. And what I've come to realize is that some of those methods which are particularly popular shouldn't really be used. So I didn't understand the problems for a long time, and I'll explain how I discovered the problem in the first place, that the flat band potential I was measuring couldn't have possibly been the real flat band potential. So to resolve this issue, I embarked on a systematic study where I looked at the main techniques that had been mentioned in the literature for several decades for the measurement of this value. And then I applied them to a set of electrodes that I synthesized, and then I compared the results to try and understand what's going on. So the four techniques that I used, so the one that you'll probably be familiar with if you work on semiconducting photoelectrodes. So it's impedance measurements for Mott-Schottky analysis, so capacitance as a function of applied potential. Then we have the photocurrent squared, which, according to the Gettner-Butler equation, which is that idealized kinetic curve that doesn't account for any losses, if you extrapolate the linear portion of that curve to the x-axis, the x-axis intercept gives you the flat band potential in theory. Then there's the case of doing chopped photocurrent measurements, so transient measurements where a potential is modified and light is chopped on and off. And the point there is to detect which way the bands are bending, because they bend in different directions, either side of the flat band potential. And so if you detect that crossover, you can find the flat band potential. Very difficult to do if you don't have a lock-in amplifier. And finally, open circuit potential, which at first I thought, well, why is everybody bothering with the Mott-Schottky analysis when you can just measure the open circuit potential at higher radiance, take the value, and that's your flat band potential. It's really easy. And then I discovered why it's not so easy. So what's my problem with the Mott-Schottky analysis? So we have had a potentiostat. It was a Metro Motor Lab potentiostat coupled with a frequency response analyzer, which you need to do impedance measurements. And the software that came with it had a function that said, oh, Mott-Schottky analysis. We thought, well, brilliant. Okay, we'll do that. We'll do everything that this procedure says, and we'll find the flat band potential. Wonderful. And of course, this procedure wanted you to select a frequency of the perturbation at which you wanted to plot the Modt-Schottky graph that you can then extrapolate to find your flat band potential. So we tried several frequencies, and this is what we got. So by the way, not everybody gets such a huge dispersion, but we looked at this and thought, well, where's the flat band potential? Okay, you have some kind of p-type behavior where oxygen evolution occurs, so let's just ignore that and focus on the n-type behavior. And then we put, lines of best fit through all of these curves and didn't arrive at a single value of doping density or at a single intercept. So we thought, well, we can't use this. It's just not reasonable. So we then started looking more closely into the literature, and we found that just for synthetic hematite electrodes, so if we just scan the values that are highlighted in red, under the same conditions, over quite a small range of doping densities, the values of the flat band potential, if you convert them to the same, relative to the same electrode, reference electrode, they span, 0.8 of a volt? I mean, that's a huge dispersion in values. In fact, we thought, well, this renders kind of these values completely meaningless because there's something really wrong here. There cannot be such a dispersion in flat band potentials because it's just not justified by the doping density or the electrolyte compositions, which were more or less the same for all of these systems. So to sort of do a spoiler alert, what happened at the end of our study when we looked at everything with Modt-Schottky and the other 4 techniques, this is what we found. So let's just plot electrode potentials on the x-axis, right? So just arbitrarily ranging from minus 0.9 versus the standard hydrogen electrode to plus 0.5. Let's mark where the solvent boundaries are. Just an example at pH 14, because that's corresponds to about 1 molar hydroxide solution, which is what most researchers use for hematite because that's where it performs best and that's where it's chemically stable. So these are separated by a favorite value of 1.23 volts. So if we take all the literature values that I just showed in the table, that is the range that they span. So you're kind of not quite bridging the 1.23 volts as solvent stability, but it's a very significant dispersion. So then what I did is I had 3 identical hematite electrodes and I did the same measurements for all of them, just, to check that it wasn't one electrode that was faulty and the rest were, just to get an idea of reproducibility. And what I found that with all of our 4 techniques, if you combine all the data, this was the range of flat band potential values. So the difficulty and the reason this work took something like 6 years to complete is because we really struggled to explain why every technique was giving, values that were so extreme. And most importantly, which one was most reliable. So in terms of the 4 techniques, if we measured the open circuit potential without any scavengers, so let's say 1 mole of sodium hydroxide, we got a really neat range of values, almost believable. When we then put in a scavenger, so I think it was hydrogen peroxide, we got a slightly higher dispersion, but the values were, a fair bit different, so considerably more negative. And we thought, oh, okay, well, maybe with the scavenger, that's the real value. Maybe it prevents Fermi level pinning or something like that. And then we did Modt-Schottky, and the values were way to the negative side, which is kind of, I would say, was more consistent with the bulk of the literature. But those values didn't overlap at all with the open circuit potentials. Then we did chopped photocurrent without scavenger, which was more negative than OCP. So already we thought, well, the OCP values can't possibly be true. The ones that gave the most similar responses was the chopped photocurrent measurements. So at this point, we realized that transient measurements were probably the better way to go than steady state measurements. And so what I ended up advocating is that you should use several techniques to verify the flat band potential values before, for example, publishing them. But also some techniques are definitely more trustworthy than others. So OCP is not one of them. And finally, with the Gertner-Butler analysis, so where you have the photocurrent squared, we're completely the other side of the value, so hugely positive. And this is without any scavenger, and with the scavenger, we're actually more in line with the chopped photocurrent measurements. So this was the picture we had, and as I say, the task was to explain why. So this basically got us looking at the structure of the semiconductor liquid interface. So if I sort of draw let's say, just one version of what a photoelectrolyzer might look like. In this case, you have 2 photoelectrodes. These don't necessarily have to have a semiconductor liquid junction, but in our case, we had a semiconductor liquid junction, which is what was making everything more complicated. So if we zoom in on such a junction, okay, this is what it comprises. It comprises of a semiconductor on one side and a liquid on the other side of the interface. So the trick with, or rather the difficulty with the system is that the energy levels of the two systems are characterized by completely different scales. So the semiconductor has all of its energy levels, reported and calculated on the physical scale. So, in units of electron volts, and everything's measured relative to vacuum. So conduction band electron affinity is relative to vacuum, and so on. Whereas on the liquid side, we have potentials that are actually measured relative to a reference electrode, the potential of which is fixed relative to vacuum. So it starts to become basically a puzzle to align all of these, to align these two scales together. And what we discovered, because we were unable to do this, so I kept calculating the flat band potential of hematite that was way positive of the conduction band, whereas it should have been more negative so that it would actually lie between the conduction and valence band. And I thought, well, either the conduction band energy is wrong, which may well have been the case, because it's, as a first attempt, it's estimated based on electronegativities of the constituent atoms and just an assumed average band gap. But the flat band potentials were so high above the conduction band that if it was true, you should have, probably seen spontaneous hydrogen evolution happening on hematite. And we know that that's not the case. So being completely unable to align these scales, sort of confirmed that there was something really missing in this picture. And that something is also missing from representations like this, when you get bands of the semiconductor being plotted both against vacuum and versus the standard hydrogen electrode. So there's always an assumed offset, but actually that offset is not the same for the different semiconductors, and it's not constant at different potentials. So it actually changes. Why does it change? Because at the interface, you have the band bending of the semiconductor, which we all know happens, but you also have a potential drop across the Helmholtz layer, so that your actual total interfacial potential is a sum of the band bending in the semiconductor and the potential drop across this Helmholtz layer. So in this depiction, I've basically positioned the solid phase, which is a semiconductor, right in contact with the liquid phase. I've indicated where the reference electrode is, the bulk electrolyte, and the Helmholtz layer. So it's not a particularly pleasant diagram, but I hope that the bits that I've sort of highlighted in blue, which say total interfacial potential, highlight that there is another contribution to the interface. And this potential drop across the Helmholtz layer, it very much depends on what pH you're at and how that solution pH differs from the pH of zero charge for a particular semiconductor. So in this picture here, we have a higher, more alkaline pH than pH PZC. And so you have this kind of potential drop across the Helmholtz layer. The gradient would be reversed if we were in more acidic solutions. The only case when there would be no potential drop across the Helmholtz layer would be at the pH of zero charge. So a very specific condition, which doesn't really coincide with the conditions under which, for example, hematite is usually employed. So that got us looking back at papers that were published in the 1970s, where they actually, tried to model this interface. And the book that was particularly helpful to me was by Pleskov and Gurevich, where they had essentially a derivation of how these two phases contribute to the overall interfacial potential drop. So that's what I started following through in my methodology to try and understand how an externally applied electrode potential modifies this scenario, and how that might be basically linked back to our huge dispersion in the results. So what I wanted just to very quickly recap is how these experiments are done, right? So what you're doing in an electrochemical experiment in the typical 3-electrode setup is you're using a reference electrode to measure the Fermi level of the semiconductor. So that's what you're measuring. That value changes when you have an offset in the Helmholtz layer, right? And then on top of that, so this is at the flat band condition. And then on top of that, you start to interfere. When you apply a potential, you start to modify the band bending, right? So you can, for example, in this scenario, you have a working semiconductor electrode and then an electrolyte. Then you have the bulk of the semiconductor, the bulk of the electrolyte. And then you have those interfacial regions where things are different. So you've got the semiconductor space charge layer and the Helmholtz layer. So the question is, well, what happens in the Helmholtz layer? So in this, what happens in the space charge layer, for example, is if you have let's say an N-type semiconductor, the bands are bent upwards, so you've got accumulation of electrons. When you gradually bend the bands downward, you pass through a stage where there's no band bending. That would be a flat band potential. And then you bend them the other way and you start to have depletion. So this is the condition at which you have oxygen evolution happening on N-type semiconductor electrodes. And the question is, how do we probe what happens at the Helmholtz layer while this goes on? So it cannot really be done without actually going through and modeling everything, because when you measure the overall capacitance of this interface, for example, this is what you do with Mott-Schottky experiments, that if you ever determine the flat band potential is probably something that you've done, you've got two contributions to that. You've got the capacitance of the space charge layer and the capacitance of the Helmholtz layer. So everybody always assumes that the capacitance of the Helmholtz layer is so much larger than the capacitance of the semiconductor that it's completely irrelevant to the measurements. But what has become clear through the modeling is that that's not the case for highly doped semiconductors. And the other aspect is that it's often assumed that all of the applied potential is actually dropped across the semiconductor space charge layer, because the electrolytes are concentrated, and so there shouldn't be a significant drop across the Helmholtz layer. But again, when we think about what happens at a metal-liquid interface, a metal is a conductor, right? So there is virtually no potential drop across the metal, and all of the potential drop is across the Helmholtz layer. That's how most electrochemistry that doesn't involve semiconductors works. So when you have a poorly doped semiconductor, yes, the Helmholtz layer doesn't get a high drop across it. But when we have the kinds of semiconducting photoelectrodes that are being developed these days that are actually quite highly doped, a lot of them are actually quasi-metallic, which means that it's not surprising, or it cannot be assumed, that none of the applied potential goes across the Helmholtz layer. So how can we illustrate this? So the model that I mentioned, which I'm not going to go through all the equations on the screen because that's terribly boring, but I put in the reference here to Pliskov and Gurevich. If you follow through the model and you plot what an ideal Mott-Schottky plot should look like. So on the x-axis, you've got the semiconductor band bending. On the y-axis, you've got 1 over the square of the capacitance. So that's your typical Mott-Schottky plot. And we've calculated the plot for a donor density of 10 to the 26 per meter cubed. So that's a very high value. Okay, so of course the intercept of that goes to where you have a semiconductor band bending of 0. So you basically just have to figure out at what electrode potential that condition is from experiments, and you're done. But if you stop ignoring the capacitance of the Helmholtz layer and take some of the values that are being reported in the literature, depending on the actual value of the Helmholtz capacitance, the Mott-Schottky plots would look something like this. So the green one at the bottom is for when you assume that the capacitance is infinitely high and doesn't contribute. And then you have some of the published values. So you can see that for a highly doped semiconductor, the actual resultant Mott-Schottky plot looks very different. And actually, these look a fair bit more like what you actually see in publications. Now, it's rare to actually have a complete Mott-Schottky plot over such a huge potential range. So normally you get some sort of linear plot over a small potential range and you extrapolate. So where would we extrapolate these plots? So that one goes to 0, but depending on which part of the plot you've got in front of you, you can extrapolate basically to anywhere. And this might explain why in reality you get such negative values for when you use the Mott-Schottky technique, and why when you convert them to the physical scale, it seems to correspond to a really high energy that cannot possibly be realistic. So the reasons for this are, first of all, that the capacitance of the Helmholtz layer cannot be ignored. And the additional factor that also messes with the Mott-Schottky approach is the fact that the applied potential is not distributed always across the semiconductor layer only. So what we've got here is a total applied interfacial bias. So the total applied across the semiconductor and the Helmholtz layer. And on the y-axis, we've got the fraction of that applied bias that goes to the Helmholtz layer. And we can see, unsurprisingly, that the more heavily doped the semiconductor is, the higher the fraction that's distributed across the Helmholtz layer. And that's consistent with, approach to quasi-metallic, approach to metallic behavior. And so, of course, this causes a total modification of how the Mott-Schottky plot, Mott-Schottky values are aligned with the applied potential values. So the gradients become completely unrealistic. And so the way this modifies the plots, so you can compare what the Mott-Schottky plots look like if you ignore the potential drop across the Helmholtz layer and when you take it into account. And you can see that for low doping levels, it doesn't matter too much. So that's the blue curve. But for high doping levels, that's the orange curve, the plots look completely different. So what it shows is that when you look at your experimentally determined Mott-Schottky plot, you are, without modeling, unable to distinguish how that plot is impacted by the potential distribution across the semiconductor and the Helmholtz layer, and how much the Helmholtz capacitance contributes. So the latter can be accounted for, but the stretch across the x-axis is very difficult to do without a model. So that's the story with the Mott-Schottky plots. I hope this sort of summarizes why in addition to actually working out the capacitance values from impedance measurements, interpreting the data can be associated with a lot of error if you don't actually have information about your semiconductor, like accurately knowing the doping density, which if you were to get it from the slope of these plots would be incorrect. So it has to be determined using some other methods. When we do the photocurrent squared, it's obvious that recombination actually plays a very big role in the data that you can see. So if you don't have some sort of charge scavenger, recombination causes a very positive onset in the photocurrent, which is obviously the problem with a lot of semiconducting photoelectrodes. There's too much recombination, cannot beat it, and so the photocurrent flows at very high potentials, which sort of start to negate the benefit of having a photoelectrode in the first place. And even when you use a scavenger, such as this H2O2, you can see that even there you have a slight S-shaped behavior over small band bending. And these values are completely different. So if you were to just do this using a whole scavenger, is that the true flat band potential? Well, I think the point here is that you really have to use several techniques and they have to agree for there to be any certainty about the flat band potential value. And just to illustrate that, the Gertner-Butler equation from which this technique was actually derived also assumes that there's no potential drop across the Helmholtz layer. And if you were to introduce that, the kinetics look very, very different. And if you were to account for the Helmholtz layer, which that's what you have when you look at your experimental data, you can see that the shift in the determined flat band goes in the positive direction. So in the case of Mott-Schottky, you get overly negative values, and in the case of this photocurrent squared, you get overly positive values. So that goes some way, only thanks to the model, this goes some way to explaining the large dispersion in those values that are plotted against the solvent stability range of water. And finally, the OCP values, these were so well behaved. I mean, they asymptoted so nicely with irradiance. We thought the bands were completely unbent, but as we determined with other techniques, there must have been some sort of Fermi level pinning occurring due to, whatever. That makes this really nice, straightforward technique, unfortunately, not very reliable, although it would have been very nice. And finally, the chopped photocurrent squared technique. This one is actually, we did this manually, so all of these chopping were done with a with a credit card. So we had a steady light source. We did this with white light. We did this with monochromatic light, and we basically scanned the potential really, really slowly, 1 millivolt per second, from negative values to positive values. And we manually chopped the light on and off about once every 3 seconds. And what we were quite interested to see is that apart from this main region for hematite, where, which we all know, the photocurrent is where you expect it to see. What we also saw, if you look at what happens at about minus 0.2 volts, is that there is an additional region of photocurrent. And that's definitely anodic photocurrent. So having looked at that, we were like, okay, well, the flat band has to be negative of that. So eventually, through very laborious experiments, it's not visible, actually. It's not very clear from this plot, but we found the potential of transition from cathodic photocurrent, even on hematite, very small, transitioning to anodic photocurrent. And it happened at more negative potentials than OCP values dictated or showed. So we became quite convinced that this transient method was probably the most appropriate. And perhaps instead of doing it manually, this is something that could be done with a lock-in amplifier so that the chopping is done manually. It also gives a photocurrent, which is in no way a steady photocurrent, but it will give a very clear transition from cathodic to anodic behavior. So this is something that we were converged on as being a particularly useful technique to use, and also simpler than the Mott-Schottky method. So I know I'm already at 45 minutes, but I just wanted to very quickly introduce the work that my colleague Frankie continued. So this was the work with all the flat band potential. So having done all of that just to determine the flat band potential, then have to model the rest of the kinetics that accurately account for all of the losses that happen. So the bulk recombination efficiency, the surface recombination efficiency, that's a function of applied potential. And then in some cases, there's also the Faradaic efficiency. So what fraction of the total current actually is the process that you want? And it's not always 100%. So Frankie, unlike me, I investigated only on 3 electrode samples. Frankie made 20. And for each and every one of those samples, he computed the charge transfer efficiency using a myriad of different techniques. So he used some DC techniques and some AC techniques, and he got really excited. So for DC techniques, he used transient photocurrent. So this is the chopped photocurrent that I just showed a slide ago. And from there, you can see the difference between the current spike from the rush of charge to the stable photocurrent, the constant photocurrent that flows. And then you can also do things like we did with recording photocurrent as a function of applied potential when you put, for example, a scavenger into the solution. So that could be used to determine the bulk recombination ratio relative to when you don't have sacrificial reagents. And then the stuff that's a little bit out of my area of expertise, because I've never actually personally done these experiments, one of these experiments or the analysis. But in terms of AC techniques, we've got the photoelectrochemical impedance spectroscopy, which is the same as normal electrochemical impedance spectroscopy, but when you shine light. And then Frankie did intensity modulated photocurrent spectroscopy. And he did all kinds of different analyses on this system. So not just equivalent circuit fitting, which is what you can do if you want to avoid this use of single frequencies for Mott-Schottky, but also things like distribution of relaxation times, which is something that he discussed a lot with his collaborator Dino Klotz. And he was able to do this really systematic study using spray pyrolyzed tin-doped hematite on FTO. He used a consistent electrolyte, so either 1 molar hydroxide or 1 molar hydroxide with scavenger. Same reference electrode, which he checked that it remained stable for all the measurements. Platinum wire counter electrode. And then instead of white light, he used LED, which he concluded actually gave a more stable light source. He determined that even use of mechanical shutters, for example, for chopped measurements, introduced enough error, i.e. too slow. So introduced enough error that affected the efficiencies that he actually calculated in the end. He covered the same range of potentials. He used different light intensities for the chrono experiments, and modulated all of those light intensities as well for the IMPS approach. And this distribution of relaxation times is something that can be done with a freely available tool, but it has to be downloaded online. It's quite complicated to do from scratch. But Frankie, if anyone wants his details to discuss the intricacies of this, I'm happy to provide them afterwards. But this is the grand graph that he got. So there's all these legends showing different ways in which data was analyzed, but essentially he combined all of these techniques to calculate that recombination fraction that causes that S shape in photocurrents when you're close to flat band potential. So as you move away from the flat band potential, recombination losses decrease, but in that transition region, they are quite difficult to calculate. But probably I would say that any of these results would be good enough when it comes to putting this kinetic model into a multi-physics model to design reactors, because there is no significant impact of this on the predicted photocurrent densities, or at least their magnitude. But if you are really trying to compare one material against the other, you really need to know your material very well and your technique very well, and use multiple samples to be confident that the technique you're using is giving reliable values. So what Frankie concluded, that actually chopped photocurrent measurements are probably the most reliable measurement, and that using sacrificial reagents actually introduces more error than is apparent from the results that actually look very neat at first glance. So Frankie calculated this as a function of electrode potential, and also subsequently as a function of light intensity. So the accuracy of the technique depends on light intensity and depends on potential. So some techniques that are accurate in one range of conditions are not necessarily the best ones. So having done this for hematite, it remains to be seen how these results might actually compare with, other materials. But I must say that Frankie had a real trouble publishing this paper because it was deemed very apparently uninteresting, and reviewers wanted like 10 other materials to be analyzed in the same way. But it didn't happen in the end, but I'm pleased that it's finally been accepted in Electrochemical Character. I don't think we've got the DOI for it yet, but hopefully soon. Anyways, I guess it's for very interested people who really want to understand what's going on at the interface. But I guess this is important when, for example, you're making new materials and you want to comment on, well, did certain dopants really shift the flat band potential or not? Or did they really affect the efficiency? I mean, you really have to go to some length to be able to make reliable conclusions. So what Frankie concluded is that transient photocurrents offer the most reliable results. Sacrificial reagents actually give less reproducible results, and that whether you're using intensity modulated photoelectric spectroscopy or photoelectrochemical impedance spectroscopy, more or less the results are actually quite all right. And what he's done is he proposed a strategy, which I know there's some abbreviations here, for which I should have probably provided a code, but it will be available in the paper when it comes out, is kind of a proposed algorithm strategy about what measurement is best to use depending on what you've got available and what you're observing on your electrode during kind of these first few simple tests that you do. So for example, do you get current doubling? That's something that could be ascertained quite easily before you go to all the trouble of doing this complicated analysis. So I think I'll stop here in case anyone has questions. I was going to go on about my my remaining passion in this area, which is trying to model tunneling currents in the dark. But I think I will leave it here. And yeah, thank you very much again for listening, and I'd be very happy to take any questions.
Thank you, Helen, for very nice talk and the exciting talk. We have some questions of Sergio Lázaro. Thank you, Helen, for your presentation. We understand that the light decreases the potential because of the electricitation. It is correct. It's a cooperative effect.
Think presentation. So is this for the open circuit potential measurements? Yes. So if this refers to the open circuit potential measurements, so light, so higher intensity light introduces more electrons into the conduction band, right? So this causes the unbending of bands to a point where any more light doesn't make any change. So yes, I think if I understood that question correctly, then I think so. I think I'm reading the question. That is the next one from Joao. Congrats on your work. Beside the electrode simulation, have you done any combined temperature simulations to see how the total current is affected? So I have not personally done this. I know that a few of my colleagues have attempted it, I've not read the paper because they somehow never published it, but I think that they showed that temperature did not have any beneficial impact on hematite. But definitely there was a very convoluted effect between everything. So it's not like you increase temperature and everything else lines up in a really nice trend. There's very few trends here. It's probably the most mind-boggling thing I've ever come across this. It bothered me for years. I couldn't figure it out. Right. From the point of view of finite element simulation, would it be possible to obtain an arrangement for the electrodes that minimizes the potential drop? Oh, yeah. Yeah, that's the whole point. So the potential drops are caused by resistivities of the electrode substrate. So, for example, if you use this FTO or fluorine doped tin oxide, it's okay if you have a centimeter square electrode. It's not okay if you scale it up to 50 square centimeters. You can't do that without suffering losses. So that's why I guess people like Van der Kroll and Ibi Ahmed, they do metallic grids on FTO and then put the semiconductor down like you would do in solar cells to try and prevent the current losses. And then, so in addition to the substrate, there's then the electrolyte resistivity, right? And how you arrange your electrodes. So all of that is exactly what finite element modeling helps to solve. And so so there's so many ways in which you can arrange the electrodes. Ideally, they face each other, but then you need the conductive substrate. Then you get the resistive losses. You can have perforated electrodes, but that involves, if you have perforations through all your semiconducting layers, the chances that there won't be corrosion are quite small. So it's one of those over-constrained problems, right? Which is why photoelectrochemical reactors are still not exactly being deployed. It's because there are material constraints and engineering constraints. And the question is it so over-constrained that finding something optimum is, well, we'll see how possible it is. But of course, everyone knows that the bottleneck is still the materials, right? There are a few materials like hematite and bismuth vanadate that probably are okay, stable, give okay photocurrents, but in terms of photocathodes, I'm not aware of anything that's sufficiently stable and sufficiently well performing for upscaled water splitting. But so I don't actually develop materials myself, nor Frankie, whom I mentioned. We sort of synthesized the materials. They're not the best performing, but they allowed us to do all these investigations because they were kind of, I guess, giving some nice, stable but curious behavior. So we're not really in the business of developing materials. So for that, we're hoping to collaborate with others on their titanic efforts to synthesize materials, and then we design reactors to incorporate them. That's kind of the plan. And then we see if we can make the reactors work. I mean, my personal preference is to try concentrating the light. Not necessarily using like massive parabolic dishes, like the one, for example, Sophia Hausener has a TPFL, because the concentration factor is so high that you really need quite extreme temperature management there. But I'm hoping for sort of smaller scale Fresnel lens concentrators to see if we can decrease the constraints on making the electrode super big in 2 dimensions, because it's very difficult to synthesize uniform films and it's difficult to avoid resistive losses. Okay.
I have a question. Cyril?
Is it time? Shall I read out the last one, or is it too late? Have studied any possible modification of the electrode during the measurements to evaluate? Yes, we investigated that. So with the hematite electrodes, we made nothing happened. We pushed them to like 3 volts. We looked at SEM and what's the one called? So the word escapes me, but the really fancy solid state measurement. I don't remember. The ones that gives all the energies of the orbitals. I forget. Anyway, we did a lot of studies to show that nothing happens to these electrodes at all. So that's the one solid conclusion we can make. But that's the good thing about hematite. Right.
Yeah. Yeah. Thank you very much for your presentation. Nice presentation, Hannah. I invited you to see the flash presentation now. Thank you, Hannah.
Thank you so much. Thank you for listening to me. I'm afraid I have to go because I'm interviewing undergraduate admissions. I have to go interview poor school pupils for admissions to Imperial, but I will rewatch the video later.
Okay. Thank
Thank
you.
you
Thank
so
you,
much.
Hannah.
Thank you.
Bye,
Thanks,
bye,
everyone.
bye.
Bye.